the Grimes teacher here, and let's take a look at 2006 higher level question 12c. Whoa there, cowboy. Slow down, pause the video, and take 10 minutes to attempt it because it's half of a full question. 10 minutes is more than enough. Regulate. A lovely question on specific heat capacity, and one that's worth 28 marks, so it was worth half of a question that year, but lovely stuff to it, so let's take a look. First off, define power and define specific heat capacity. So since he doesn't label the sections, I'm going to call this A, this section B with the calculations, and then this section C down here, right? So let's have a look at defining power. So I'm going to call it A, but you can see it's C part 1. But there's two C part 1, so that's why it's confusing. So power is the rate at which work is done. Which work is done. Excuse my handwriting, but you can hear me say it. How do you say that in equations? Work over time. Now this is in the formula booklet on page 58. When you give an equation, make sure to give him, by him I mean the examiner, the units. So there's work W, power P, and time T. When you're giving the units, when you're giving the symbols as well, make sure you tell them the units. So that is power. Power is measured in watts. Work is measured in joules, and time is measured in seconds. And that would be a perfect answer in your Leaving Cert. A lot of students ask me, Steve, can I just write the equation and write this here? And I'm going to say, yeah, you can get away with it a lot of the times, but always I would be encouraging my students to learn the definition because you need to understand it as well. Part 2 of that same part said specific heat capacity. So define specific heat capacity. So specific heat capacity is the amount of heat energy needed to change the temperature of 1 kilogram by 1 Kelvin. So it's the heat energy needed to change 1 kilogram of a substance by 1 Kelvin. You'll sometimes see some books say 1 Celsius, and I'm going to say not a big deal. The examiner's not going to really dock you or kill you for that. Technically it's 1 Kelvin if we're going to be super technical and nerdy about it, but there's no need to get stressed about it. E equals mc delta theta is the equation for specific heat capacity, and make sure to read the question because he could also ask you heat capacity on its own. And again, if you're to give the units and do all that stuff here, E is for energy, measured in joules. M is for mass, measured in kg. C is for specific heat capacity, and you might not know the unit, so I'm going to talk about how to find that real quick here. And then delta theta is for change in temperature, and again, like I said, that should be technically in Kelvin. You will see some books do it as degrees Celsius. I wouldn't lose sleep over it. Now, how do I find this unit if I don't know it? And this goes for any section, right? If you don't know a unit, make it the subject of the equation. So here I'm going to divide both sides by m and delta theta. So I end up getting that C equals E over m delta theta. And from this you can find the unit. E is measured in joules, M is measured in kg, and delta theta is measured in Kelvin. Since they're on the bottom of the equation, if I want to bring them up beside the joules at the end, I'll end up getting this. I'll just bring it all together. Joules, kg minus 1, Kelvin minus 1. And that would be my unit for specific heat capacity. So I'll just put it there as well. I'm going overkill with my explanations here, by the way. Of course, if you just put the definition or if you put the equation in words, you quite often be rewarded, and we'll look at the mark scheme just to see if that's true in a while. Okay, so that's our first part done. Definitions accounting for 9 marks in this question. So just on context, 9 out of 28 would be approximately 32% of the equation of the question is on definitions. Okay, so don't neglect your definitions. Right, let's look at the maths. 400 grams of water at a temperature of 15 degrees Celsius is placed in an electric kettle. The power rating of the kettle is 3 kilowatts. right? Why has he told us this? Look at how he's leading us into a question, by the way. He's telling us all this stuff. Probably going to have to use specific heat capacity. Probably going to have to use power. Right. Calculate the energy required to raise the temperature of the water to 100 degrees. So let's have a look. So I'm calling it the B part, but you can call it, well, you didn't have to call it anything that year. The examiner would just have to figure it out. And nowadays he labels it better. But I've got 400 grams of water at a temperature of 15 in the kettle, and the power rating is 3 kilowatts. So let's write down everything we have. So mass is 400 grams. Now, get into good habits. You're going to divide that by 1,000 to write it into kilograms. So it's 0.4. So instead of that, I'm going to say it's 0.4 kg. The temperature initial was 15 degrees Celsius, and the temperature final is 100. You don't need to write this part. You can just write delta theta is the difference between 100 and 15 is 85 degrees Celsius. What else did he tell me in the question, or he or they or the examiner? The power rating of the kettle is 3 kilowatts, so the power is 3 by 10 to the 3 watts. If you're not sure where I got that 10 to the 3, okay, what you need to do is open your formula booklet and turn to page 45 of your formula booklet, and on that page you will find all the prefixes, okay? So you look up the prefix for kilo, and it is 10 to the 3. So the little k there, and it gives that to you on page 45 of the formula booklet. Okay, back to the question. Find the energy raised to the energy required to raise the temperature. So if we're talking about raising temperature, we're talking about mc delta theta. So let's do that. So E equals mc delta theta. E equals the mass, which is 0.4, by C, which I'm going to guess is in the question, by 100. So flick back up. Where is this C business, the specific heat capacity? I don't see it, and then I have to remind myself, oh yeah. The examiner sneaks it in at the end of the problem quite often. So in this year, he used 4,200, slightly less accurate value than the 4,180, but I'll use the value the examiner gave me. I plug it in. Oh, sorry. Moving too fast, too furious. This is a temperature change of 85. I'd already calculated that there. So just check that there. And also look, I put that in degrees Celsius again. Like I said, it could be Kelvin, or it should be Kelvin. Again, he's not going to dock you for that little mistake. It's only in the answer where he cares about the units. E equals 142,800 joules. So that is my part 1. I have found the energy required in joules. Okay, part 2, the energy supplied by the kettle per second. Now this one really stumped people. The energy supplied by the kettle per second. And it's something to do with this power business here. So let's just talk through this. And this is honestly so ridiculous. It's ridiculous. If the power is 3 by 10 to the 3 watts, another way of saying that is it's 3,000 watts, just to talk a bit easier. What that means is a watt, right? Power is defined as work over time. Or another way I often get people to think about it is energy over time, just because the W confuses people, right? That means if I have 10 watts, that means 10 joules per second. That's what something is saying. So if something takes 10 watts, it means it takes 10 joules per second to run. So if something is 3,000 watts, then it means it takes 3,000 joules per second. So 3,000 joules per second. So back to the question. The energy supplied by the kettle per second, the answer is just 3,000 joules. You can say per second or not, it doesn't matter, but just kind of a weird, or not a weird question, caught people out. They thought they'd do calculations, not at all. So just 3,000 joules per second. Find the least amount of time it would take to heat the water. We know the total energy required, and we know the energy per second, so I'm going to say the total energy. You don't need to make an equation, by the way, I'm just trying to put it in words for you. Total energy divided by the energy per second. So that becomes 142,800 over 3,000. So grab your calculator, plug it in, and I get that it's 47.6 seconds. That is the minimum time that would be required, the least amount of time to heat the water to 100 degrees. Okay, just have a check through that you've done everything he's asked, or they've asked, and sure enough I have. And this is always something I'll recommend to go as you're ticking away. In reality, the time taken to heat the water will be greater. Explain why. Now, it's a 4-mark question, which usually just means he's probably looking for 1 good point, but feel free to give him 2 if you can think of 2. I'm going to say energy loss to the surroundings. Seems like a logical one. Energy loss to the surroundings. Also, the kettle will absorb some energy. Remember, it's a container. What else could I say? It will absorb energy, or you could say some energy lost by evaporation. You only need 1 point here, most likely, I'm going to say, to get the marks. And that is us done for 2006 higher level question 12c. So let's have a little look through and see how we did in the mark scheme. So to find power, work done per second, or rate at which work is done. So rate at which work is done, that's what I had done. And it is work done per second as well. You can plug that in for extra safety. Like I said here, without knowing, being there that year, can I say whether or not they would have awarded the marks if you put the equation? I can't say, so I think you should always learn the definition. Energy required to raise the temperature of 1 kilogram of a substance by 1, and like I said here, 1 Kelvin or 1 degree Celsius, both were accepted. Heat energy needed to change 1 kilogram of substance by 1 Kelvin. Nope. That was bold. Look, and it's good to make mistakes, and I'm always one to highlight my own mistakes. To change, what did I forget? Key word in here, the temperature of 1 kilogram of a substance. That's sad. I would have lost 3 marks, okay? Because I'm going too fast. So be careful there. I didn't mention the temperature, so make sure you are, okay? E equals mc delta theta. My equation, fine, but again, looks like I wouldn't have got any marks for plugging in the equation that year. I do, though, on the other hand, get marks down here in part 1 for having the equation and for getting to my answer. So let's have a look. I get 1.428, and he's done it by 10 to the 5, but that's the same thing here. So full marks there, 3,000 joules or 3,000 joules per second, full marks. And here 47.6 seconds or 48 seconds. And again, just watch your units. Did we have our units here? Did, so all golden, okay. Energy lost, last bit, energy lost the surroundings, or the kettle absorbed it, or lost by evaporation. Any of those would have done well. So there you go. Always just have a check like that in the last few minutes of your exam. Go through and check things like that. I'm not even going to remove this from the video, even though I made a mistake, because honestly, it's worth seeing how if you're going a little bit too fast. I probably said it, but I didn't write it. And at the end of the day, it's why you're writing the page. Okay. That's 2006 question 12 part C with a specific heat capacity and power question. Best of luck in your Leaving Cert. Hope you found that useful. If you did, then like or subscribe, or check out the other social medias where I'll be adding extra resources. If you want something particular made, then just leave me a message on one of those platforms and I'll do my best to get around to it at some point. Best of luck in all your exams.